So thank you for having me. So today I'm going to be talking about aligning spikes to the brains with the IBL GUI. So this is a tool that we've developed as part of the IBL. And it's basically an additional step that you can add onto the end of the histology pipeline that was just presented. And it allows you to use electrophysiology data that you recorded on your probe to basically improve the estimate of where your recording electrodes are in the brain. So first, I just wanted to do a quick recap of the full histology pipeline so you can see where this extra step fits in. So as we just presented, using tools such as Brain Globe, you can, once you have your 3D image stack or indeed your kind of 2D individual histology slices, what you want to do is basically warp them and transform them such that they can be registered to this common coordinate reference atlas that the Allen Institute has provided. So once you've done that, you then want to, so hopefully if you've labeled your probe nicely with the dye, you should see these very bright fluorescent tracks. And what you can do is use tools such as Brain Globe to manually trace the location of these probes in the brain. And you can join these points up to get then a 3D reconstruction of your track in the brain. Once you have that, you can then distribute your electrodes along this track according to the channel map that you used, so the kind of arrangement of electrodes that you used for your recording. And in this way, we can then get a first estimate of where our electrodes are in the brain. So we have the XYZ coordinate of all of our individual electrodes. And because we are in this common coordinate framework that the Allen has provided, each XYZ coordinate corresponds to a specific volume in this voxel, and each voxel has a brain region annotated to it. And so this way, we can now say we think that our recording electrodes were located in these brain regions. So you could go ahead and use these brain regions for your analysis, and this would be like, for example, the output of Brain Globe. But there's one extra step that we could also do to account for a few different inaccuracies. And these arise from the following reasons. So the first is that when we warp all of our atlases onto this common coordinate framework, what we're doing is basically shifting the different brain regions to match this template atlas, and this allows us to collate data across different subjects. But in doing that, we basically lose the individual differences between brains. So this could be the difference in brain sizes, but also the difference in distribution between the different brain structures that will be unique to given subjects. There's also inaccuracies in the tracing step. So this tends to be a manual process. And so either when you're doing it manually, it could be that you could not locate the tip of your probe, for example, if the dye is underexpressed or overexpressed. There can also be diffusion of the dye, which means that it kind of bleeds into the neighboring tissue, so you can't really identify exactly the probe tip. And another case of this is, for example, I think Carolina was mentioning yesterday, how if you insert your probe too deep into the brain, if you're targeting deep structures and you find that the probe bends, you then will need to retract your probe, but you've already labeled the tissue beneath this. And so in this case, you have a bit of uncertainty in exactly where your probe tip ended up. So to account for these things, what we can do is add an extra step at the end where we basically loop in or use the electrophysiology data that we recorded on our probe and use features that we can extract from that to basically use as extra information to estimate where our electrodes should be in the brain. So this diagram here shows the concept behind this. So on the left-hand side, we have our neuropixel probe and the brain regions that it passes through. And on the right-hand side, we show the firing rate that we've recorded across the session on this probe. So you can see that we have this area here that has a very low firing rate activity. And based on our prior knowledge, we expect that this should come from a region that has very few or no neurons. And if we inspect the histology, we can see that we have this white area here, and this corresponds to an air gap in the brain. So what we want to do is basically use reference signs that we can add on both the histology and also the electrophysiology, and use these to basically shift the location of our electrodes in the brain such that the histology landmarks match our electrophysiology landmarks. So you can see here in this example, we've basically shifted the location of our electrodes up in the brain. So here we've just applied an offset, but in reality, we also want the ability to scale our electrodes linearly across the brain, but also scale them within specific regions. So there's a number of different electrophysiology features that you can use to do these alignments. And this paper here by Liu et al. Kind of describes the whole histological process, but it also has a nice summary of the different features you can look out for. So they have a table of the different landmarks and also the feature that you expect to see. So for example, the brain surface or ventricles, you expect there to be very low activity because there aren't very many neurons and a reduced LFP power. Another useful feature is these pyramidal cell layers. So these typically are in the CA1 and also layer 5 of the cortex. And these typically have a very high activity high amplitude and high activity firing rate spikes. And another one, there are others. So for example, the boundary between the hippocampus and the thalamus is also a useful reference. So I just wanted to show one example of these features. So another one that actually wasn't in this table, but the dentate gyrus is a very useful feature. So this is in the hippocampus and has two very distinctive features. So the one is that it's got this very high power in the LFP band. So here we're showing the LFP's power spectral density overlaid on the geometry of the probe. And we can see that here in the dentate gyrus, we have this very, very bright yellow area, which shows that it's got very high power. The other thing that's characteristic of this region is that it's often sandwiched by these two molecular layers, so the dentate gyrus MO. And here we don't have any kind of firing neurons because it's a molecular layer. So you can see in the firing rate activity across the probe that we have this high activity region that's sandwiched between these two silent layers. So these kind of give examples of the kind of features that you want to be looking out for when you're doing the alignment. So I will now give you a demo of the tool that we've developed at the IBL that allows you to do this. So the basic idea is that we show a number of different electrophysiology plots that you can see on the left-hand side. And then in the center, we show the histology image. So there are two histology kind of the areas where the probe passes through the brain. So the one on the left, you're going to find as you do your alignment, it's going to shift and move. And the one on the right will stay constant. And this is just so you can reference to the original annotation and see how much you've changed things. We also show a coronal slice, which is useful to see sometimes the channels in the anatomical context, because sometimes these 2D interpretations, you can kind of lose track of the actual anatomy itself. So on the top, we have these menu options that allow you to change the plot that's being displayed. So we're showing the cross-correlation of activity, the RMS of the LFP band, and we also have these single unit displays where you can click on the individual clusters or neurons and see their waveforms and also their autocorrelograms. And so looking back to Julie's talk earlier, like you can look for characteristic waveforms, for example, axonal ones in the fiber tracks. And these are different features that you can look out for. So you can also change the probe plots. So there are lots of drop-down menus that allow you to change the different plots that you display. And you can zoom in, for example, on displays to see things in more detail. So everything in this GUI is based on these reference lines that I was using or referring to earlier, and these can be added to the display by double-clicking. And you get a pair of lines that move independently on the electrophysiology and also the histology image. And the idea is that you want to drag these lines to match the electrophysiology feature with the histology feature. So in this case here, what I'm using is the boundary between the hippocampus and the thalamus, and moving my lines such that they match up where I think it's good. And then I can press this fit button and it will then apply this alignment. So if you focus on the image on the right, the coronal slice, if we look before we've applied the fit and after, we can see we basically shift the location of our electrodes up in the brain. So then I can continue this and add another reference line. So in this case, I'm lining this high firing rate region here to the center of the CA1 layer in the hippocampus. And I add another reference line and then apply the fit. So in this case, we've not only applied an offset, but because we have two reference lines, we're also applying a scaling. So you can see in the central panel here, so this light blue area here indicates a scaling factor that you applied to the different regions. So you can continue to add as many reference lines as you see fit to continue with the alignment. And once you're happy with it, you can then press this upload button. And it will then save the new channel locations on disk in like a JSON file that you can then access and read in to do your analysis. So finally, I just wanted to give you a summary, or kind of give you an idea of what kind of scaling factors and offsets are expected. So using this tool in the IBL, we actually went through and aligned over 700 different insertions. So thank you to all the experimenters for their work to do that. And I've summarized the amount of scaling that we've applied to the different brain regions. So here I've coarsely kind of grouped the brain regions according to quite coarse areas. So for example, the isocortex, the hippocampus, the thalamus, the hindbrain. And on the y-axis, it's showing the scaling factor that's been applied to each of these regions. So scaling factor of 1 indicates that we haven't scaled the region at all. And what we find is that in general, we're basically shrinking the region slightly. So I think on average, it's around 0.97 scale factor that's applied kind of across all regions. And this basically indicates that compared to our original distribution of our electrodes, our electrodes actually span a larger portion of the brain than we initially estimate just via the probe tracing. Here on the right, I also show the average offset that we've applied. So this is comparing the location of the tip of the probe prior and after alignment. And in general, we see that we basically shift the probe up slightly in the brain, so around 50 micrometers. But what's interesting is also there's quite a large span. So obviously sometimes the tracing hasn't gone so successfully. And so in this case, we adjust for this during this alignment process. Yeah, so just to conclude, I have a page full of resources that you can use that have links to this tool that we've developed. So there's a GitHub repo, and there's also an associated wiki. And in this, it will have install instructions of how you can install the GUI. And there's a page of how you can use it, so describing the different plots that are available and the different shortcuts and tools that you can do, features that are available. And there's also this section about how you can prepare your own data for the GUI. So basically how you can transform the data that you have such that it can be read in and you can display it. So what you need to provide is your spike sorting output, preferably your raw data as well, so we can then extract some of the features such as the LFP and the RMS AP. And also you then need to provide the kind of the trace probe track that you've done, that you've manually tracked. In one of the labs associated with the IBL, there was also a summer intern whose project was mainly just doing a lot of alignment, and she's actually written a very nice blog going into the nuances and the learning she found. So if you're getting started, it's quite a nice place to see the kind of considerations that you need to do when you're starting to do these alignments. So with that, I'd just like to thank the IBL and all of our sponsors for supporting this work.